Hello, everyone. My name is Shri, and I'm from Johns Hopkins University. I'll be presenting on this flexible multi-layer tactile sensor on a soft robotic fingertip. In our lab, we work with a lot of upper limb prosthetics. As amputations increase, thousands of amputations every year, is a growing population of amputees who need a replacement limb. And over the last few decades, with myoelectric prosthesis, we've gotten pretty good. It's come quite a long way at replacing that lost function by creating these complex mechatronic devices, basically robotic arms. However, it's only replacing one side of the lost function. And so what we're trying to do is also add sensory feedback, try to replace that lost function and to fully close that loop. And so part of this motivation is that tactile sensing is an integral aspect of interacting with the environment, with texture information being essential to properly manipulate objects. And so as we interact with these objects, we receive both static and dynamic cues. And that's usually through this tactile sensing. So static cues such as temperature or force can usually be sensed instantaneously. However, they're not as feature-rich as dynamic cues, which allow users to more actively interact with their environment. However, processing these dynamic cues, such as surface textures, is more complex because it requires more static and dynamic information. So as a secondary part to this, also soft robotic fingers are a compliant biomimetic solution for these upper limb prostheses. So soft robots benefit from their inherent compliance, increased dexterity, low weight, and reduced costs. And therefore, by adding tactile sensing capabilities such as texture discrimination on a soft robotic finger, we can create a more compliant and dexterous prosthetic hand for an amputee. So in this study, we emulate a human fingertip by incorporating a flexible biomimetic multi-layer tactile sensor into a soft robotic fingertip for a texture discrimination test. And so this work is a step in the direction of creating a more human-like prosthetic hand that can help amputees and enhance amputees' perception and interaction with their environment. So in this paper mainly focused on the sensing side, less on the soft robotics. And so the flexible multi-layer sensor, we try to mimic the, biomimetic layers of the tactile sensor. They were inspired by the mechanoreceptors found in human skin. The mechanoreceptors are what measure the mechanical stimuli in our fingertips. And to the outer piezoresistive sensor array, so that's layer A, they represent the Merkel cells, which provide touch information, and the Meissner corpuscle, which provides low frequency vibration information. So the outer layer, layer A, tries to mimic the epidermis. The middle piezoresistive layer tries to mimic the Ruffini endings. And so these Ruffini endings, they generally measure the deformation. And finally, the inner sensor layer is a piezoelectric disc. And that's just a commercial sensor. And that was used to mimic the Pacinian corpuscles, which is, again, lies in the dermis. And those detect transient pressures and high frequency vibrations. And so this tactile sensor, all three layers, were integrated into the soft robotic fingertip, which is mainly fabricated out of silicone and 3D printed plastic. And the blue section is where that 3D printed plastic is, which is like a rigid piece. And so that's mimicking the fingernail of our fingers. Again, the focus is mainly on the fingertip, which has a sensing component. So the outer and middle layers, like I mentioned, they're piezoresistive sensors. And so they're made out of fabric. So it's a piezoresistive fabric that's sandwiched by conductive fabric traces. And so the outer layer, so that's part A, is a 3x3 sensor array. So it has 9 sensing elements that are 4 millimeters square in size each. The middle layer is a 3x2 sensor array. And so these have so 6 sensing elements, and they have a larger sensing surface of 9 millimeters square. So it's slightly larger as it's deeper level. And the inner layer is a commercial 10 millimeter piezoelectric disc that's adhered to the underside of that rigid fingernail. So it's right in contact with the rigid piece. And says overall, we characterize the sensor layers independently before we actually put it in the finger. And so the average of each of the sensor layers are shown by the line, with the error bars showing the actual numbers of the surrounding sensing elements. And so the inner sensing, so if you notice that inner layer is missing from this, and that's because that piezoelectric sensor only responds to the onset of force, and so detects the transient pressures and high frequency vibrations, similar to Pacinian corpuscles, and so it doesn't map exactly the same way. It's more saturates, just as things happen, it responds. And so I guess the actual characterization, again, since it's a commercial sensor in that sense, it's 3 to 5 kilohertz resonant frequency with the max resonant impedance of 300 ohms. So the second part of how we create this biomimetic sensor, first is actually trying to do physical layers by mimicking the fingertip. The second part, what we're trying to do is using neuromorphic encoding. And so these tactile sensors or the tactile responses from each of these layers were neuromorphically encoded relative to the skin's mechanoreceptors using the Iskarous neuron model. And so the neuromorphic encoding as a system, it's an encoding method that's used to model and mimic the dynamic neuronal activity of nerves. And so this is basically how our nerves communicate, which is, in this case, action potentials, spike trains. And so the biomimetic approach of using neuromorphic encoding is both biologically relevant for afferent nerve stimulation. So again, when we try to close that loop, one side is sensing, the other part is electrical stimulation, or giving that stimulation back. And so by now translating all this information into how nerves actually, or neurons actually function and communicate, it makes the process of stimulation more direct. And the second part is also it increases the computational efficiency by encoding this information in the way that, I guess, is more biological. So each of these neuromorphic models, so in the figure, the 4 different lines, they were chosen based on their similarities to the spiking responses of those corresponding mechanoreceptors. And so by using the 3 equations, the neuromorphic model generates a spike train based on the voltage that's, in this case, the input current. We use the voltage of the sensor response as input current into these equations. And so the parameters A, B, C, and D, they regulate the behavior of that spiking models. That's what helps map it to the different types of spiking models. And finally, we have K is the gain that's used to increase the sensitivity for each model. And so the outer piezoresistive layer, that was encoded using the tonic spiking model, which is what mimics this SA1 system. And so SA1 is slowly adapting. And so it's that just to be able to mimic it, like I mentioned, similar methods. The Meissner corpuscle is fast adapting, so that's what FA1 is. And so that's using the phasic bursting model. And so they have these types of models were established by the Iskarous spiking network, that framework. The middle piezoresistive layer was encoded using the fast spiking model, which is SA2, that mimics the Ruffini endings. And finally, the Pacinian corpuscle was encoded using the phasic spiking model, which mimics the FA2 fast spiking secondary model. And so after we create these spike trains basically out of the sensor response, that's still this large amount of information. So we try to compress some of that using 2 spike-based metrics. One is the mean spike rate, and the other is the average interspike. The mean spike rate is just within the window. What's the average number of spikes within the entire window? The interspike interval is what's the timing between those spikes. And so these are two metrics that's used in neuroscience usually for collecting as much information about the spiking responses and action potentials. And so we use this similar testing method, or not testing, this similar compression method to try to get the most information out of it in sort of in a simplified way. And so these, the mean spike rate and the interspike interval from the different spike trains were used as the features for the classifier. And so to test these, the actual texture discrimination, we go over 13 different texture plates, passively palpating over it. And we create, it's sampled at 1,000 samples per second. And so we have these 13 different textures that are trying to mimic, varied types of spatial and temporal information, because that's what needs to be picked up for these sensors. Let's speed up a little bit. And so finally, we use those features into the SVM classifier. So we use SVM because it's a support vector machine. And so we use that because it's been shown previously, both in our work and outside, of doing really well with these, with texture discrimination. And then we reduced the bias. We did k-folds cross-validation with the K of 4. And then we also reduced it further by running it 1,000 times. And to really compare the real benefits of having the different layers, we show, so with the multi-layer sensor, it works really well. It's like a 97% classification accuracy. It has no issues with basically with these textures. But as we start reducing the number of layers, or looking at it individually, you can see that it starts dropping down with lots of information. And so that's whereby, so compared to these accuracies of each layer independently, this biomimetic sensor does benefit from having those multiple layers. So in conclusion, right, so this flexible biomimetic multi-layer tactile sensor array is using neuromorphic encoding on a soft robotic fingertip capable of texture discrimination. And so as part of texture discrimination in general and using this neuromorphic encoding, the exact forces at each sensing element is not as relevant as much as the transient changes as it goes over the texture plates. That's where that spatial and that temporal information becomes really important. And so with neuromorphic encoding, we're able to capture both that spatial and temporal information in a simple system. And so again, this is the overall goal of trying to get this to close the loop for amputees and have a full prosthetic hand that's a replacement to what the lost limb function is. So the potential to try to allow amputees to better perceive and interact with their environment. Thank you. Any questions?